Hello everyone, welcome to Lab 6 on root locus techniques. So what we're doing this week is we're looking at root locus and what it is a way of plotting the poles of a system with respect to some uh, variance of a system parameter like k. So if we have something like this, where we have a k value here and we can change that to be whatever, it's just a scalar. Then we have some function g, and maybe we have a function a in the feedback path. We can simplify it to this thing, and then we can find the root locus based off of the roots of the denominator, otherwise known as the poles of the system, right? That's a big concept right there. The roots of the denominator are the same as the poles of the system. So that's what the root locus is. We're going to plot the poles of the system by looking at this guy here and solving for it equals to 0. Okay. Last lab, we did a root locus plot kind of from scratch, and that was cool. But you can actually do it using a function called rlocus. But we need to be very careful with what this system is. So I'll talk about what this input is specifically. Make sure I'm recording. Yep, okay. Let's do an example. So here we have this type of thing going on. We have k times g. We've kind of lumped it together into g. And then we have this h in the feedback path. So what we're going to do is we're going to simplify it down using this formula here, right? So then we have this guy. And we're going to look at the denominator and find the roots of the denominator, or, right, the poles of the system. Same thing. But we're going to look at the denominator. So here's the denominator. Again, the root locus is the location of the poles of the closed loop system with respect to k. So here it is. We'll note that I'm just going to do some algebra here. Whoops, right here. And we'll note that the s that makes this equation work depends on what k is. So there's no one answer for the poles of the system. They're going to change depending on what k is. And that's what we found out in the last lab. We changed k, and then we looked at the poles and plotted the poles. So for example, if k is equal to 0, then it's pretty easy to see how the poles of the system are going to be 0, -2, and -3. Right? Okay, so that's cool, right? We can kind of do this by hand by plugging in different values of k, but that would take forever to make a plot. So we're going to use MATLAB instead. We're going to use the rlocus function, and the function just takes a system input. You might also want to specify k, but you don't really have to specify k. MATLAB will just kind of figure that out for you. So here's the we need to know what the system input is. What it is this gh term here. So we have the denominator in the form 1 plus k times some function or functions. Right, that's what we get here. 1 plus k times some function or functions. And that, in this case, is gh. Right, so here's gh. This is our system that we're going to put into the root locus, or rlocus. And we'll plot it. So that's what we do in MATLAB. Here we go. Here it is. I'll run that. Here we go. Ta-da, here it is. What you can do is you can drag your cursor along these poles, and you can see how you get a specific gain value associated with it, or that's also the k value. So the gain value and the k value are one and the same. A pole value associated with it, you can get a frequency associated with it, overshoot, and damping. These are all very important characteristics to know. Let's say you want a system with a certain damping. Well, then you can just drag this along until you find that value. Say you want a damping of 0.3, right? You go here, that's about 0.3. We want a gain of 41, right? Pretty useful. Just to validate that when k equals 0, we get 0, -2, -3. When the gain is 0 here, we get -3. When the gain is 0 here, we get -2, and also we get 0. So that's great, that works out. Moving on to residue, totally different topic. Oh, wait, I'll also say one more thing. So the slide has this thing called rlocfind. you don't need to use that. What it does is it gives you some crosshairs. You can kind of snipe what point you want to look at, and it'll spit out the root and the frequency. But why do that when you can just drag this little point around, right? This is way better. So just ignore that, rlog find. Okay, so residue. Let's say you want to make a partial fraction expansion of a transfer function. Why would you want to do this? Well, if you want to turn a transfer function into the time domain, then you want to use the inverse Laplace, right? And to do an inverse Laplace, you need a recognizable form, right? If you're doing this by hand. And this is a very recognizable form. This partial fraction expansion term is in a table somewhere. So you want to turn, say, this thing here into a partial fraction expansion. And so how you do that is you get this form here, right? You get this form here, and you need all the r values and the p values, and maybe you have some non-zero k. And so pretty straightforward. You say residue, numerator, denominator, right? Numerator, denominator, and it spits out the r values, p values, and k values. So here they are here. I'll run it in MATLAB as well. Here they are. Okay, so now we can, make this thing here. But if our goal really is to plot this thing in the time domain, we need to know what we're inputting to the system, right? Because if we're not inputting anything, our response isn't going to do anything. It's like if we have a pendulum and it's just sitting at rest and we don't input anything to it, it's just going to sit there. It's not going to do anything interesting. We're just going to get a bunch of zeros. But say if we apply a constant torque to the system, otherwise known as like a step function, we're going to get something a little bit more interesting, right? So the frequency domain equivalent of a step is 1 over s. So remember how we have this form, r of s goes into our closed loop transfer function, and what comes out of that is our response, right? So our r of s is our input. That's our input torque. And so, right, if we get into this form here, we say r of s is 1 over s, right? That's the same as the step. We multiply across. Now we can go ahead and do the inverse Laplace of this guy and get a response in the time domain, because we know what the system is and we know what the input is. So here it is. Here's the input, 1 over s. Here's our partial fraction expansion with all the terms that we found in MATLAB. And we're going to do an inverse Laplace in MATLAB. We're going to plot it, and we're going to compare it with something that we're familiar with using LSIM. Okay, so here in MATLAB, I've defined a symbolic s. I'm going to combine these terms together just like I do here using this for loop. Right, these are our r values, here's our p values, and our k turns out is 0, so we don't have to worry about putting that on the end. We're going to take the inverse Laplace of that whole thing. I'll note I also went ahead and multiplied by 1 over s, so there's an s squared here and an s here. Right, so I've taken care of the input. Okay, inverse Laplace, we're going to plot it from 0 to 5. Seems like a good range. And then we're also going to plot it using LSIM. And LSIM is something you should be familiar with. Our input's going to be a step, right? In the time domain, that looks like a bunch of ones. That's what this is. We're going to go from 0 to 5, and we'll see what we get. Okay, we get the same thing. So that's very neat. We've done the residue function to find the partial fraction expansion. We did the inverse Laplace and with a step input, and we've come out with this thing here. And then we've also done an LSIM, which is taking it directly from a frequency domain system and inputting a forcing function and a time function. So that's very cool. We'll end on sensitivity. What sensitivity is it is how the poles of a system change depending on how your k value changes. So let's say you're at some k value, 20 point something. You have your transfer function. The poles can be found in the denominator, right? The roots of the denominator are the same as the poles of the system, right? So we just need the denominator here. So we have this k value, we have the denominator, and we can find the roots for this specific k value. Then we're going to change the k value by 5%, and we get a new k value, km, and we are going to plug that into kind of this new system, right, just with this updated k value, and we're going to get a second root. So we've gone through once, we've got with a k value of 20 point something, and we found the roots for that. We've upped it by 5%, found the new roots. What we're going to do then is subtract the roots from each other, get a delta root, and then we know the decay, right? That's this 5%. So that's, this part makes sense, right? It's how much does your roots change with respect to how much your poles are changing, or your k is changing, and then you're going to normalize the whole thing by k. And do I have anything on that? Yeah, I do. Whoops. Here it is. So here's our sensitivities. Why are there 3 sensitivities? Well, there's 3 different poles. So not all the poles have the same sensitivity. Like one pole might be changing a whole lot depending on, how much you change your k value, and another pole might only change a little bit when you change the k value. And again, this is going to depend on where you're starting at, right? If k is 100, your sensitivities for certain poles might change. So just be aware of that. Okay, so I'll leave you guys to do the tasks, and I'll see you on Wednesday. This week, I have to be a little bit more strict on how much direct help I can provide on lab tasks, because people are doing too well on the labs, and we need a curve. So unfortunately, I am not going to be validating any tasks this week. I can give you example problems and I can work through those, but I can't say, okay, this is correct, say for a given task. Okay, so with that, I'll see you guys on Wednesday.